Welcome to the Explainer. Today we are diving into a really mind-bending idea. What if the very structure of our thoughts, our minds, actually follows the rules of a strange and beautiful kind of geometry? Okay, so let's start with this central mystery. This is a huge question, right? How does any complex system, think of an ecosystem or even your own mind, manage to stay creative and flexible without just completely falling apart into chaos? Well, the answer, and this is pretty surprising, might just come from pure mathematics. So to get our heads around this, we're first going to have to build something, a kind of geometric playground. And believe it or not, we can do it with nothing more than paper and glue. I want you to imagine taking a simple square piece of paper. Now, glue the left edge to the right edge and the top edge to the bottom. What you get is a donut shape, or what's called a torus, that is perfectly flat almost everywhere. It's kind of like an old school video game map. If you walk off one side, you just reappear on the other. So, mathematicians have a name for this. They call it a translation surface. It's basically a world with really simple rules. The most important one? Straight lines stay straight, and they just keep going, forever. This perfect simplicity is what makes it an amazing stage for exploring the hidden rules of really complex movement. All right, so we've built our world. Now what happens when something actually moves in it? Well, the answer is somehow both simpler and way, way stranger than you might think. We can actually understand this motion with a really simple analogy. Imagine you have a ruler. You cut it into a few pieces, and then you just shuffle those pieces into a new order. That's it. This shuffling process is what mathematicians call an interval exchange transformation. Okay, so here's the really crucial connection. The path of a straight line moving through our two-dimensional paper world casts a kind of one-dimensional shadow. And the pattern of that shadow, it's exactly the same as our ruler game. This is huge because it means we can understand the complicated 2D motion just by looking at this much simpler 1D shuffling process. And this is where the real mystery kicks in. If you keep doing this, if you keep shuffling that ruler over and over and over again, what do you think you'd see? For the longest time, everyone, and I mean everyone, thought the answer was obvious. You'd get pure, unpredictable chaos. So, for decades, mathematicians were expecting chaos. But then, a stunning discovery revealed something else entirely. Something nobody saw coming. A deep, rigid order hiding just beneath the surface. This is the best analogy for what happens. You expect to get a chaotic, random cloud of dust when you shake the box, but instead, what you get is structure. The dust settles into these elegant, perfectly flat sheets. It's like the system, no matter how much you shake it, has this incredible hidden desire to be simple and organized.
This discovery has a name. It's the Eskin-Mirzakhani theorem. It was a truly astonishing piece of work by Alex Eskin and the absolutely brilliant Miriam Mirzakhani. What they proved is that these systems, the ones everyone thought were totally chaotic, are actually incredibly rigid. They don't just wander around randomly. They're stuck in these very specific, highly structured spaces. And that changes everything.
Now, you might be thinking, okay, that's cool for math, but what does it have to do with me? Well, this isn't just abstract number crunching. It turns out to be an incredibly powerful model for understanding our own minds. Let's see how this geometry actually maps onto our internal world. Look at this. This slide shows a direct one-to-one mapping between the mathematical objects and our own minds. So a quadratic differential in the math world, that's like a core belief or a constraint in your thinking. The translation surface, that flat paper world we built, that's your imagination, the space where you run simulations. And a straight line flow is just a single thought or an action. So you see, this isn't just a loose metaphor. It's a structural model of how we think. So what happens when this geometric map breaks down? If a healthy mind has this rich, complex geometry, what does an unhealthy one look like? Okay, this is the most crucial takeaway of the whole explainer. Failure in a system, pathology, it's not about being too chaotic or too stressed or moving too much. It's about losing geometric richness. Pathology is a collapse in the system's available degrees of freedom. It's a loss of dimension. So, a healthy system, whether we're talking about a mind or an ecosystem, has this rich geometry. It's what allows it to be flexible, to be creative, to explore. It can handle stress by making these temporary little trips. Scientists call this allostasis, and then it comes right back to a stable balance. A pathological system, on the other hand, has suffered a geometric collapse. It's become brittle, rigid, trapped. Instead of exploring possibilities, its motion is funneled into these super narrow channels, or it just breaks apart and becomes fragmented. It can't adapt because its internal map, its geometry, has lost its richness. And this is amazing. The math gives us a precise way to understand these failures. This slide shows how specific types of geometric collapse lead to very distinct problems. When the geometry pinches in just one spot, you get things like chronic rigidity or compulsive loops. When it pinches in lots of different places, the system fragments, which can lead to dissociation. And that leaves us with a final, and I think really profound question. If getting sick, if pathology, is a process of geometric collapse, then what does it mean to heal? Maybe, just maybe, healing isn't about reducing stress or finding calm. Maybe healing is the act of rebuilding our internal geometric worlds, restoring their richness, their complexity, and their freedom to move.